നമുക്കിനി matrix representation of angular momentum നോക്കാം. There are many ways to represent angular momentum operators and their eigenstates. Now we are going to discuss the matrix representation of angular momentum, where the eigenstates and operators will be represented by column vectors and square matrices that we have already discussed. Since J square Jz commute, the set of their common eigenstate set of eigenstate Jm can be chosen as a basis. This basis is discrete and orthonormal and complete. And the completeness condition can be expressed as summation m equal to minus j2 plus j get jm bra jm equal to I. This is the completeness condition. ഇത് വളരെ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള ഒരു ടേമാണ്, നിങ്ങൾ ശ്രദ്ധിച്ച് നോക്കുക കേട്ടോ. Then where I is the unit matrix, the operator j square and jz are diagonal in the basis given by their joint eigenstates. And we have seen that j prime m prime j square jm can be expressed as h cross square j into j plus 1 delta j prime j delta m prime m delta. Okay. Then j prime m prime jz jm can be expressed as h cross m. This is the eigenvalue h cross m delta j prime j delta m prime m. Thus the matrices representing j square and jz in the set of basis jm eigenbases are diagonal. The diagonal elements being equal to h cross square j into j plus 1 and h cross m respectively. Now since the operators j plus or minus m do not commute with jz, they are represented in the set of jm basis by the matrices that are not diagonal. The elements are bracket j prime m prime j plus or minus jm equal to h cross square root of j into j plus j plus 1 minus m into m plus or minus 1 delta j prime j delta m prime m plus or minus 1. And we can also find the matrices of the jx and jy as bracket j prime m prime jx jm equal to h cross square by 2 square root of j into j plus 1 minus m into m plus 1 delta m prime m plus 1 plus j into j plus 1 minus m into m minus 1 delta m prime m minus 1 delta j prime j bracket j prime m prime jy get jm equal to h cross square h cross by 2I square root j into j plus 1 minus m into m plus 1 delta m prime m plus 1 minus j into j plus 1 minus m into m minus 1 delta m prime m minus 1 delta j prime j. So these are the elements of the matrices, and a model is given in this problem. Just find the matrices representing the operators. Just solve this problem and it is easily understood. If you have any doubts, you can contact me. Then spin angular momentum. In addition to the orbital angular momentum, the electron possesses an intrinsic angular momentum which unlike the orbital angular momentum has nothing to do with the spatial degrees of freedom. We have already done that. You have already know that the electron has intrinsic spin. This intrinsic degree of freedom was given the suggestive name of spin angular momentum. And the spin an intrinsic degree of freedom is a purely quantum mechanical concept with no classical analog. Unlike the orbital angular momentum, the spin cannot be described by a differential operator. The orbital magnetic dipole mu L is equal to q by 2 mcl for orbital, and for spin also we can write as mu s equal to q by 2 mcs, where mu s is equal to minus gs e by 2 mec. Yes, gs is called the Landis factor or zero magnetic ratio. By analogy with the orbital angular momentum of a particle, which is characterized by two quantum numbers, the orbital L and the azimuthal quantum number ML, where ml varies from minus L to plus L. The spin angular momentum is also characterized by two quantum numbers, the spin s and its projection ms on the z axis. In nature, it turns out that every fundamental particle has a specific spin. Some particles have integer spins s equal to 0, 1, 2, and so on. Example, pi mesons have spin s equal to 0. The photons have spin s equal to 1 and so on. And the others have a half-odd integer spins s equal to 1 by 2, 3 by 2, 5 by 2, and so on. Example, electrons, protons, and neutrons have spins s equal to 1 by 2. The deltas have spins s equal to 3 by 2, and so on. And you have already seen half-odd integer and bosons and fermions like that. The general theory of spins. The theory of spin is identical to the general theory of angular momentum. നമ്മൾ നേരത്തെ L ന് പകരം നമ്മളിവിടെ we use S. By analogy with the vector angular momentum J, the spin is also represented by the vector operator S, whose components Sx, Sy, Sez obey the same commutation relations as Jx, Jy, J. അപ്പോൾ നമ്മൾ Jx അല്ലെങ്കിൽ Lx നെ L നെ പഠിച്ച അതേ കമ്മ്യൂട്ടേറ്റർ എല്ലാ റിലേഷനും ഇവിടെ നമുക്ക് ഉപയോഗപ്പെടുത്താം. സിമ്പിൾ മാത്രമേ മാറ്റുന്നുള്ളൂ. അപ്പോൾ കമ്മ്യൂട്ടേറ്റർ എസ് എക്സ് എക്സ് വൈ ഈസ് ഈക്വൽ ടു ഐ എച്ച് ക്രോസ് എസ് ഇ സെഡ്, കമ്മ്യൂട്ടേറ്റർ എസ് വൈ എസ് ഇ സെഡ് ഈക്വൽ ടു ഐ എച്ച് ക്രോസ് എസ് എക്സ്, കമ്മ്യൂട്ടേറ്റർ എസ് ഇ സെഡ് എസ് എക്സ് ഈക്വൽ ടു ഐ എച്ച് ക്രോസ് എസ് വൈ. Then s square get s ms equal to h cross s into s plus 1 get sms. Then SEZ get SMS equal to h cross ms sms. And ms varies from minus s to plus s. And ladder operators is given the operation of s plus or minus acting on the get sms the same h cross square root s into s plus 1 minus ms into ms plus or minus 1 s ms plus or minus 1. Then expectation value is given here. Then for a particle with spin half, the quantum number ms takes only two values, ms equal to minus half and plus half. The particles can thus be found in either the following two states. Get sms equal to get 1 by 2 1 by 2 and get 1 by 2 minus 1 by 2. The eigenvalues of s square and sez are given by s square get 1 by 2 plus half plus or minus 1 by 2 equal to 3 by 4 h cross square get 1 by 2 plus or minus 1 by 2. Sez get 1 by 2 plus or minus 1 by 2 equal to plus or minus h cross by 2 get 1 by 2 plus or minus 1 by 2. Then the matrix elements are given here. For s square, it is 3h cross square by 4 1 0 0 1. Sez is equal to h cross by 2 1 0 0 minus 1. The matrices s plus and s minus is given by s plus is equal to h cross 0 1 0 0. S minus is equal to h cross 0 0 1 0. And Sx is h cross by 2 0 1 1 0. Sy is equal to h cross by 2 0 minus I 0. And these s square Sez are expressed in terms of two element column matrices known as spinors. That is get 1 by 2 1 by 2 we can express as 1 0, get 1 by 2 minus 1 by 2 as 0 1. These are spinors. Then Pauli matrices. When S equal to 1 by 2, it is convenient to introduce the Pauli matrices sigma x, sigma y, sigma z, which are related to the spin vectors as follows. S equal to h cross by 2 sigma, where sigma x is equal to 0 1 1 0, sigma y 0 minus I 0, sigma z equal to 1 0 0 minus 1. These matrices satisfy the following two properties: sigma j square equal to I, sigma j sigma k plus sigma k sigma j equal to 0. These two equations are equivalent to the anti-commutation relation set of sigma j anti-commutator sigma j sigma k equal to 2I delta j delta k. And we can verify the Pauli's matrices satisfying the commutation relation commutator sigma j sigma k equal to 2I epsilon j k l sigma l. The epsilon sigma j k l is anti-symmetric tensor known as Levi-Civita tensor, and the Levi-Civita symbol is given is equal to 1 if jkl is an even permutation of x, y, z, minus 1 if jkl is an odd permutation of x, y, z, 0 if any two indices among jkl are equal. And the Pauli matrices are Hermitian and have determinants equal to minus 1. Sigma j dagger equal to sigma j. Transpose of sigma j equal to 0. Determinant of sigma j equal to minus 1. Using the relation sigma x, sigma y, I, sigma z along with sigma z square equal to I, we can write sigma x, sigma y, sigma z equal to I, sigma I. അപ്പോൾ ഇത് നിങ്ങൾ ഇതിൻ്റെ മെട്രിക്സ് ഫോർമേഷൻ ഒക്കെ എഴുതിയിട്ട് നിങ്ങൾ മൾട്ടിപ്ലൈ ചെയ്ത് നോക്കണം കേട്ടോ. അതിപ്പോൾ വായിച്ചു പോകുന്നുള്ളൂ. നിങ്ങൾ പെന്നും പേപ്പറും എടുത്തിട്ട് ഇത് ഓരോന്ന് എഴുതി നോക്കുക. അപ്പോൾ ഇഫ് യു സ്റ്റക്ക് എനിവർ യു ക്യാൻ കോൺടാക്ട് മീ. ഓക്കെ, നമുക്കിനി അഡീഷൻ ഓഫ് ആംഗുലർ മൊമെന്റം ഡിസ്കസ് ചെയ്യാം.